Let me see what we could do. All right. So just a quick review on what we covered so far. We covered oscillations. We talked about systems. What's a free oscillation and what is needed for an object to oscillate, right? We talked mainly about simple harmonic motion and this major relationship here for simple harmonic motion to occur, right? We talked about the difference between simple harmonic and circular. We talked about these equations here to show the difference between displacement, velocity, and acceleration. Remember, if you have displacement, you differentiate down, right? In case you can't differentiate, you learn the equations I gave you there. We talked about maximum velocity. We talked about the graphs, how the graphs related. We looked at how to determine if a body moves with simple harmonic motion, right? We looked at developing equations like this for simple harmonic motion and so on, right? Then we had this graph here. We had this graph here for the energy change as displacement changes, right? We saw how the kinetic and potential change. We also talked about damped oscillations and the degree of damping, right? When you remove the energy from the system, here we had undamped, critically damped, lightly damped, heavy damped, right? Then we talked about adding energy to a damped system, and we had something called resonance occurring. Here's an example of what will happen when the force oscillation is applied. Then we had these examples of resonance. All right, some quick things that we kind of just want to run over. We want to run over wave motion, right? A few of the concepts of wave motion. We want to talk about phase difference, polarization, right? And I wouldn't go to stationary waves today, right? Because that's where it becomes a little bit more challenging, right? So you want to go over things that we would have done in Form 5 today, right? Wave motion and all those little things, right? So we start here today on wave motion, right? Straight from your notes, so you don't have any writing to do. Anything you don't understand, just let me know, right? So wave motion is a means of transfer of energy from one point to the other without there being a transfer of matter between the 2 points, right? Waves may be classified as being mechanical or electromagnetic. Mechanical waves are produced by a disturbance. What's an example of a wave like that? What's an example of a wave that is produced by a disturbance? Right, very good, a sound wave, right? Right, and of course a material medium is needed, right? And the energy is transmitted by the particles of the medium oscillating to and fro about an equilibrium positions, right? Mechanical waves, therefore, require a particular medium for their propagation. For example, water waves, waves on a string, sound waves, waves in a spring, like a slinky, right? Electromagnetic waves, on the other hand, those are the ones we're familiar with, like radio and microwaves and light and thing, right? They consist of a disturbance in the form of varying magnetic and electric fields. No medium is necessary. However, electromagnetic waves travel more easily through a vacuum than through matter, right? Quick little question. Anybody remember a major difference between like electromagnetic waves and mechanical waves? There's a major difference in the way the particles behave. Anybody remembers? Anybody remember? Right, good. So yeah, for the mechanical waves, for example, sound, the particles vibrate left to right, or they vibrate parallel to their direction of travel. So if they're traveling from left to right, they are also vibrating in this direction, right? I'll show you the slinky example less on. Right, so they vibrate parallel to the direction of travel. But sound wave, electromagnetic waves, they vibrate up and down while they travel perpendicular. Okay, so just remember that, right? Sound waves, they were also called longitudinal waves. And electromagnetic waves, they were also called transverse waves. All right. Electromagnetic waves consist of, right, we talk about that. Here we have some examples: radio, microwaves, the whole spectrum there, right? Right, was periodicity. A non-periodic wave or pulse consists of a single wave front and is produced by a single disturbance. A periodic wave, right, is produced by a succession of period disturbances which give rise to a wave trace. So for example, longitudinal waves, you should remember this. You have points where the waves far apart and then points where the waves are close together. Then where they far apart again, close together, far apart, right? These were called your compressions and these were called your rarefactions. All right. And then you had your transverse waves, which had a crest, trough, crest, trough, crest. Right? So you had your crest and you had your trough and so on. All right. A progressive wave is one in which there's a transfer of energy from the source to the places around it. Elements in there, right? A stationary wave is where there is no net transfer of energy, however, there's an interchange. So it might change from one form to the next, right? So we're going to focus mainly on like progressive waves today, and then we focus on the stationary waves next day. Next are the directional displacement. A transverse wave is one in which the oscillations are perpendicular to the direction of travel. Longitudinal waves, right, is in which where it is parallel, right? We talked about that already. You have your rarefactions and compressions here. We have some things to remember about waves, amplitude and wavelength and thing. If I gave you a displacement position graph, so you remember this on Form 5. If I gave you a displacement position graph, right? So you have displacement here and displacement here, right? The distance between two crests or two troughs or the length of one cycle, all of that is considered a wavelength, right? But on this graph, you cannot read off period. You need a displacement time graph to read off period. Okay, so to just some quick definitions to remember, right? Right here, right? You have your crest, you have your trough, and you have your period. But what I want to point out here between these two graphs is that the first graph is a graph of displacement versus position. So you could read off wavelength. Here is a graph of displacement versus time. So you could read off period. Can't read off wavelength, right? Okay. Right, so displacement x is the vector distance, right, on a wave particle, that's particle, from its equilibrium position. So it's this distance from the equilibrium position. Amplitude is the maximum displacement of a particle from the equilibrium position. So amplitude is the maximum displacement, right? And you could get from both graphs. Period is the time taken for a particle to undergo one complete oscillation, right? You could only get from the displacement time graph. In the period, T waves move through a distance of one wavelength. So from this here, we could develop a few formulas. So for Hodges here, right? So here's what it's saying. Actually, you can help me develop a formula for speed here. Speed of a wave. Speed is what? How do we find speed? Anybody can answer. How do we find speed? Generally. Speed is what? Very good. Speed is distance over time. All right? So here's what they're saying. In fact, use that formula and see if you can get a formula from now. Use this formula and see if we can develop the wave formula that we use in CSEC in Form 5. Try that fast. Let me see what you get. Nalia, try it, huh? Check the back again, the punching. Oh yeah, yeah. That's the formula, but I wanted to develop it. That's pretty good. All right. So here's what this says. This is saying the time taken, which is period, to cover one whole cycle is a wavelength. So the distance covered is a wavelength, and the time taken to do it is a period. So it's lambda on t. Right? So watch this here. We know that period is 1 on frequency. Right? Because frequency is the number of oscillations in 1 second. So period is 1 on f. Okay? So here we could do now, we could say that lambda is 1 on t. Right? So we could rearrange this and we'll see f is 1 on t. So what does that mean? It means that speed is equal to lambda by f. 1 on t is f. Okay? So that is where this formula came from. Right? So if ever they ask you to prove it, you can set it up like that, right? The distance covered is a wavelength and the time taken to cover the wavelength, period. Okay? So now, yeah, frequency. The frequency is also the number of waves which passes a given point per second, right? The frequency has the SI unit hertz. All right? So all those are things that we should know about a wave, right? Now we're going to focus on something called phase difference, right? Right, that's the formula. The phase of a particular point in our oscillation is a measure of the fraction of the oscillation that has been completed with respect to the other. So if you look here, we're going to do a little, I want to show you in a simulation as well, right? If you look here, there's a blue wave and a green wave. So the phase difference between them is the fraction, or this distance x, the fraction, right? Oh, sorry, wait, what happened there? Sorry, hold on. Right, so it is the fraction of the cycle in radians, right? That's why you will see a multiply by 2 pi, by which one leaves the other, okay? So if you look here, hold on, I'm gonna just stop it, right? So the phase difference between the blue and the green is that distance x, the fraction of x over lambda, multiplied by 2 pi. That's the value in radians. So let's say x was half a wave. Half a wave on a wave, that will cancel by 2 pi. A half by 2 pi is pi. So it means that the phase difference between those two waves is pi. All right, so it might look something like this. You have one wave here, right? And a half a cycle after, you have a next wave. What is up on there? A half a wave after, you have a next one. Right? So if you measure from here to here, that value is lambda on 2, half a wave. Remember that this quarter wave. This is half a wave. This is 3/4. This is a whole wave. All right. You're okay with that? You understand phase difference? Nalia, you understand phase difference? Nikila? Yeah? Okay. Right. I have a little question here. You see the saying A leading B and B leading A, but these graphs are not labeled. Anybody can help me determine which is A and which is B? So the blue, tell me if the blue is A or B. And obviously we'll figure out what the green is, right? So which one you all think leading? Blue or the green? Right? And they say A leading B. So if you figure out which one leading, that will be A. Which of these is leading? Or look at message, yeah? All you have to say, right, all you have to say is the green leading or the blue leading. And only the Panchu messaging, eh? Come on, message quick, Amelia. And Devesh. Oh gosh, I show you on your phone, Devesh. Yeah, we know A leading Amelia, but which one is A? The green or the blue? So we're trying to determine if it's a blue or if it's a green. I show you on your phone. And don't lie, yeah? God watching you. Hey, Nikash. Yeah, tell me which one you think is. We know A leading, but which one is A, blue or green? Green, blue, green, blue. Okay. At least you're guessing. Right. Right. So if you look there, you're saying green leading. All right. So let's focus on this point here. If I were to label this up, just be up in 1 second, 2 seconds, 3 seconds, and so on, right? And if you look at it closely, this particular displacement here that I am measuring, it happened in blue first. It happened when blue was 2 seconds. And then green reached here when it was 3 seconds. So what it appears here, it appears that blue is A. It looks like blue leading the green. Right? So don't get mixed up here. Right? This happened before this. So it appears that blue leading green. Y'all okay with that? All the people who pick green. You see why it's blue? Divesh? You see why it's blue? Nalia? All right. Maybe. Nalia, say maybe. Maybe. All right, Nalia, so just say maybe. You're going to help me here now. All right, there's a simulation that gave me that graph, right? That's where I got it from. Let me see if I get it back. And Leah is going to explain what happened in here. Which one was it? Let me check out physics lens. I think this was it. Now look at this. Hey, Papi, how am I supposed to see the graph? All right, so you have these two balls, right? And they're oscillating in fields. I'm going to do this now. I'm going to play it, right? So they're oscillating in fields. So obviously the graph should look like that, right? All right. Let me start over now. The phase difference at pi. Hold on. Oh Lord, let's see if I can get one. I could type one. All right, let me see if this will work, right? So the phase difference is 1, and we just calculate a phase difference of 1, right? Watch it here. Watch your waves. See that? Those waves are said to be out of phase, and the phase differences pi, right? Let me do a small calculation here. So let's pick this point and this point. That distance there is x. Remember the formula? X over lambda by 2 pi, right? X is that distance between it, right? And you should remember from here to there is half a wave. So X is half a wavelength. Okay, so if I were to draw this, that's half a wave, right? If I were to draw this, that's half a wave. So the distance between two of them is half a wave. If you're not seeing it like that, then look at this distance here to this distance here, right? I'm just making up. Let me say that's 2.5 to 7.5. That's about what, 5, right? Well, sorry, 0.25 is that reading, right? If it would a displacement graph, this is 0.75. When you minus them, you'll get 0.5, which is half of the whole thing. Okay, I just show you that it's half a wave, right? I want to convince you that it's half a wave. What has happened there? So it's half a wave multiplied by 2 pi. That will cancel, so you'll get pi. Okay, so those waves there are said to be out of phase. All right. Nalia, you follow that? All right, Nalia. So Nalia, here's what I'm gonna try to do, right? I'm going on, instead of half a wave and end up with a phase difference of pi, I want to get a phase difference of 0. I just get a point here, right? Let's multiply. What just happened to the keyboard? Hold on, I'm just trying to get 0.5. Trying to get a phase difference of all right. All right. What?
This one's like real hard. Daddy.
Yeah.
How do I use for these?
Okay, all right, stay outside. Okay, bye. Right, 0.5 phase difference. Right. So let's put them at a 0.5 phase difference, right? And let's see what the wave will look like. Right? So don't worry with the particles so much, right? Watch it there. That's what a phase difference of 0.5 pi will look like. So again, let's pick 2 points. Actually, I wanted to show you something. Okay, who leading? Blue or black? I know we start a little late, but who leading? Blue or black? What's your graph? Who hitting the spots first? Blue or black? Look, blue reaching top first, right? And look at the graph here. Look at the graph here.
It's the big one.
If you look at the graph, the blue, the blue line reaches the equilibrium point before. What's happening here? Anyway, so you measure this distance x and you divide it by lambda and multiply by 2 pi and you get your phase difference. Everybody okay with that? You're seeing the concept of phase difference and who leading and who not? Yeah? Okay. And of course, well, you will see the graph, right? It going up to maximum, coming back to 0, going down to minimum, back to 0, back to maximum, and so on, right? So, right. So once you'll understand phase difference, that's the most important thing, right? Because phase difference is something hard to see, right? So if you remember Form 5 work, when you have a phase difference of 1, right? Like you see in here, these waves are said to be, right? These waves are said to be out of phase, right? You would have done this in Form 5. Those two waves are out of phase. A crest and a trough meeting. And what has happened when a crest and a trough meet? You have, very good, you have destructive interference. So when a crest and trough meet, you have destructive interference. Okay, so that's a phase difference. Just one quick question. Suppose they were at a phase difference of 3 pi. Anybody can tell me what the graphs will look like? Think about it, and then I will draw it there. If the phase difference was 3 pi, what do you think the graphs will look like? Right, you'll give me a message of what you think. What do you all think it will look like? Phase difference of 3 pi. Before I play, tell me what you all think. The lagging wave will be lagging a lot more. No, better be specific. Try to be specific to how it will look. What do you think the 3 pi graph will look like? Try to figure out what pi was, and then 2 pi, and then that will help you. Anybody have a guess? What do you think 3 pi will look like? Right, let me see what somebody said. Wavelengths would be closer. I want a more precise answer. So work backwards. Use the phase difference formula and try to find x. Tell me what you get for x. And then that will help you figure out what the graph will look like. Right, so you have your 3 pi as a phase difference. And you're using the formula for phase difference, x over lambda is equal to, multiply by 2 pi. See if we can figure it out. I'm giving you a few minutes to think and then message what you think the answer might be, right? Anybody? Trouble? Well, again, trouble. All right. So let's see what the calculation will give us. The calculation will give us 3 pi is equal to x on lambda multiplied by 2 pi. Move this here. You will get 3 pi on 2 pi is x on lambda. So we get in 3 on 2, carry across lambda. We get an x to be 3 on 2 lambda. So here's what it's telling us. It's telling us that the waves will be separated by 1.5 wavelengths. So it'll be like this. One wave will be like this, and the next wave will start right here. 1.5 wave after. So what's going to happen here? You all will recognize this. Watch them here. See what happened there? What happened there is that you end up with the same phase difference at pi. So 3 pi on 2 is the same as pi. So it will be separated by what? It will be separated by 3 on 2 lambda. Right? But I want to show you why. Why you ended up with a same value there, right? So watch this cool thing here. Right? I'm just making a smaller scale, right? So let's say we had a wave looking like this. And the wave now going to start at that point here. Right? At that point there, that is 3 on 2 lambda. Watch what will happen here. The wave will join the wave in red. So the wave starts right there. Right? So the wave will look like this. And if you check out the phase difference here, it's the same. 3 on 2 lambda is the same. If I find the distance here, that's half a wave. So you end up with 3 on 2. 3 on 2 lambda is the same phase difference as a half lambda. They both carry the same wavelength. So what you have to remember is this. You might remember that so much, but you could remember this. If I have a wave, right? And the wave is the two waves in phase. Phase difference is 0. They will overlap each other. Let's say it has a phase difference of 2 pi. It means that when it's 2 pi, the wave will start here and then begin to oscillate. So technically, 2 pi and 0 means that they're both in phase. Now, if we were to look at a phase difference of 3 pi on 2, instead of 2 pi, we see 2 pi, we see pi on 2 pi already. Oh wait, my map's bad there earlier. Here is pi, right? The wave will look like this. That's pi. So you can see a crest meeting a trough on the outer phase. 3 pi on 2 is just before that. Sorry about that. My math was a little bad there. 3 pi on 2, right? Remember here was pi. So 3 pi on 2 means that the wave will start right down here. That's 3 pi on 2. 2 pi means the wave will start here. You're seeing that? All right, just in case I confuse you, I'm gonna start over. Right, I'm gonna just start over in case I confuse you. Right, so the wave looking like this, that's a wave, right? Right, I just want to use these lines so it wouldn't look too bad. Right, so that's a wave with 3 cycles. If the wave in phase has a phase difference of 0, it will start here and look like that, right? They would definitely overlap each other, right? So they will be in phase. If they had a phase difference of 2 pi, 2 pi is a whole cycle, right? So 2 pi is quite down here. 2 pi means it'll look like that. So pi and 2 pi, sorry, 0 and 2 pi, same phase difference. Now, if it were pi now, so here was 0, here was 2 pi, so it means that pi is in the middle here, right? That's pi. So I'm going to draw the wave for pi now. Right? That's the wave for pi. Right? And you will see crest meeting a trough. So you know that they are out of phase, right? Totally out of phase. Now, that was pi. So this is pi. This is 2 pi. Right? So 3 pi on 2 should be somewhere in the middle here. Right? So the wave will start there. And it will look something like that. So if you look here, you would see here a phase difference of 3 pi. Let's write it back here. What's that? 3 on 2 pi, right? So that's 1.5. Right? So that's what the phase difference will look like. You'll see that? And this is what it will look like. 3 pi on 2. Anybody confused? Sarah, you follow what's going on? You not seen any graphs? Oh, I keep glitching. Yeah, I realize I want to follow what's in my handwriting. Oh, shocked. All time I explain, all you see. Okay, hold on. I'm going back. I'm going to try the app one more. I'm going to try the application one more time, right? Right? It's a good simulation, so I want to show it from it. So let's gradually build up, right? Here's what you could do from it. Somebody could screenshot the graphs. So I'll put in phase, screenshot that. I'll put phase of pi on 2. So I'm going to split up all. I'm going to do pi on 2, then I'll do pi, then I'll do 3 pi on 2. right? And screenshot them for me. All right, so let's see how it comes out. Fields. Well, of course, screenshot it if you're seeing it, right? It was physics, I understand. Right. The reason I'm spending so much time is I want you all to see this, right? Because when we move on to like stationary waves and interference, I think I want you all to be able to understand the graphs. Right. So these two particles here, this graph is for phase difference of 0. Right? Somebody screenshot that from. By the way, you'll see the graph. Yes, okay, good. Screenshot that. That's the phase difference of pi, of 0, sorry. That's the phase difference of 0. Now, let's go to 0.5. All right, what you graph? Phase difference of 0.5 pi or half pi. What you graph? That's what the graph will look like. All right, again, blue lead in, right? Blue lead in, black. That's a phase difference of a half pi. Screenshot that. Let's take a look now at pi. So I go in 0, I go in pi on 2, then I'll go pi, then I'll go 3 pi on 2, then I'll go 2 pi. Right? I was mixing up 2 pi with 2.5 pi, and then 3 pi. Right? So I'm fixing it here, so we'll see it properly here. Right? So this now, let's do 1 pi. Right? There's a phase difference of 1 pi. So one leading the other by a whole pi. Right? So when blue starts and blue reach here, technically, that's when the black wave now starts. Okay? That's a phase difference of 1 pi. Now watch a phase difference of 1.5 pi. Right? Watch this here. Screenshot that. Right? And look at 1.5 pi, right? So we're going to compare these graphs just now, right? Let's just do 3 more. I'm going to do 2 pi now. Right? Screenshot 2 pi. For those who have the screenshots, 2 pi is similar to what? To 1 pi? You sure? 0. Very good. 0. 0. Right? So now we kind of clear that up. Right? 2 pi, a phase difference of 2 pi and 0 is the same phase difference. Right? Let's do one more. After 2 pi will be 2.5 pi. Look at 2.5 pi. Right? 2.5 was the same as what? .5. Very good. right? So you're kind of seeing the pattern now. So what would 3 pi be the same as? As 1 pi. Very good. So those two carry the same phase difference. And that's all kind of trying to drive home, right? So nice. Again, and we understand the concept that the blue leading and the black lagging, right? Seeing the blue leading, the blue hitting the top first before the black. All right, so nice. So we understand the concept of phase difference, right? The wave's moving, but one kind of leading the next. And how much it leading by is what we call the phase difference, right? Well, okay with the concepts, Divish, Nalia, it's trying to give trouble. So what we get through already. Y'all okay with that? Divish. Boy, get me mad. This boy always on his phone, boy. All right, so that's the concept of phase difference. It's really important that you understand and you see it, right? You not know. All right. That was phase difference. Right, we're not doing stationary waves today, right? Right. So that's the concept of phase difference. We know what is wavelength and we know what is speed, right? So you have to learn this formula for phase difference, right? Make sure you understand the concept of who leading who, right? That came in a multiple choice, right? Something new here is what's the intensity. Intensity is the rate of flow of energy per unit area. So intensity is really power over area. So if you see W per meter squared, if you see someone looking like that, that quantity is your intensity. Okay, intensity is power per unit area. And intensity is proportional to the amplitude. So the greater the amplitude, the greater the intensity, right? And the accurate relationship is intensity is proportional to amplitude squared. All right. Last thing you want to focus on is something called polarization, right? Plenty of you all have polarized glasses. And what the polarized glasses do is they reduce the intensity. We almost done, and all the do like online, all this can't focus for long, right? But I just want to explain this quick and we're done. So for example, those polarized glasses, what they do is they kind of reduce the intensity of the light coming in. So if you look at this light here, the light coming from the sun moving all over the place. Moving up, down, left, right, north, south, northeast, northwest, all them things, right? But then when it goes through the glasses, notice it only going in one direction. It only going up or down. So what it did, it polarized the wave. It reduced the intensity of the wave by reducing its amplitude, right? So if you see the formula here, if we reduce the amplitude, we reduce the intensity. So here's technically what's going on. So imagine you have a wave, a blue wave and a red wave. The blue vibrating up and down, and the red vibrating left to right. When the red try to go through the door, the red won't get through, right? Because the red vibrating in the wrong direction, but the blue vibrating in the right direction. So the blue will get through. But then if I turn it, the blue vibrating in the wrong direction. Oh no, you're not seeing the notes? Yeah, share notes. You're seeing the notes there? Mechanical waves? What? And I were talking about polarization. Anyway, at least a little listen to me, right? Now we on the whiteboard. What's going on here? Oh, you know what happened? I now see what happened. I really think I share the thing. And I talking from here and all this down here. You all seeing the notes now? Oh gosh, sorry about that. Good thing Amelia said that. I really think right? So we looked at wavelength, we looked at phase difference, right? We looked at this new one here called intensity. Intensity is power on area, right? Power on area. This is the SI unit, watts per meter squared. And the relationship is intensity is proportional to amplitude squared. All right. We're talking about polarization. Polarization is a concept that reduces the intensity. So here with these glasses here, you would recognize that this light, look at the light there, the unpolarized light, it vibrating all over the place. But when it goes through the glasses, it's a little more controlled. It vibrating mainly in one direction, or if it vibrating, it's much smaller. So the amplitude is smaller. And once the amplitude is smaller, we would have reduced the intensity. And this is basically how it works, right? Imagine you have a door and you have people whining up and down. And then you have some of them whining left and right. The ones who whining up and down, they will fit through the door. But if you're whining left and right, you can't fit through the door. So what that means is that light was polarized, right? And now, if you want to totally remove the polarize, if you want to totally polarize it, the ones who winding up and down, you can turn the door and they can't enter the door. So it means that now you fully polarize it. Okay? So that's the concept of polarization or reducing the intensity. Okay? So intensity is proportional to amplitude squared. All right? That's the concept of polarization, right? You could read up on the rest of this thing here, right? Okay, that's the concept of polarization, and you've seen it there in the graph. I just want to run through it quickly. This is superposition, right? You would have done this already. When you have two waves in phase, you have constructive. So that's the first three graphs. That first column there, right? That's these three here. In phase, constructive. These two are outer phase, so you have destructive interference. Quick question. These are outer phase, so what is the phase difference? Let's see if I remember that. What's the phase difference? Since the outer phase, what's the phase difference between A and B? One pi. What? The Pantry paying attention online. When you're in person, you don't answer so. Somebody will be distracting you. Real answer. Right? So yes, the answer is pi. The phase difference is pi, or if you remember, 3 pi. Pi or 3 pi and so on. Okay? So that is your constructive and destructive interference. Here's an example of two waves. The phase difference a little bit different. So it's not fully constructive, it's not fully constructive or destructive, but it's just in between. It's still superposition. So you have these two waves of different phase difference. You can, again, find X and work out the phase difference, right? Work out the phase difference. But this is also superposition. So when this wave meet this wave, it's superimposed here, right? I'm just making up a number so you would understand superposition, right? This is the last thing I've done all this, so let's pay attention for 2 minutes. Let's pretend the value here was, let me start here. Let's say this value was -4, then this value here might be +4. When you add it, the superposition, you get is 0. Let's say the middle here, where they both intersect, that value is 1.5. Then this wave, this dotted wave is 1.5, and this let's call that broken wave is also 1.5. When they superimpose, you get a wave with amplitude 3. That's okay? Same thing here. When you add up the value here and you add up the value here, you will get 0. When you add up the value here and the value, let's say here, you're getting this value here, right? So when you add up the displacement at a particular point in time, let's say here and here, sorry, here and here, you will get the black wave. So the black wave is the superposition of the two broken waves. Okay? That's it, right? So what we're going to do next, we're going to take a look at stationary waves, right? We started to talk about resonance, right? Resonant wave is very similar to a stationary wave. All right, so we're gonna start talking about stationary waves next day and be able to calculate them and predict when they will happen, right? Based on where you have them in openings or closed pipes or both pipes open and so on. Okay, so we're gonna take a look at that. After that, we had to focus on wave phenomenon thing, right? So next week we'll focus on that.